country with 35,000 kilometers of coastline and a fault line running down the side of it. 14,000 of those kilometers officially need protection from the sea, a coast longer than Tokyo to London and back. One town had already done it. Taro, on the Sanriku shore, built a double seawall 10 meters high and 2.5 kilometers long in an X across the bay. They called it the Great Wall of Taro, March 11, 2011. The water came over the top of it in under 2 minutes. Over, not through. Some people had climbed onto the wall to watch. Watch what they did next.
This wall is 12.5 meters high. The one it replaced was 4. We will climb to the crown.
Start with what arrived that day. A magnitude 9 earthquake 70 kilometers offshore. It moved the main island of Japan 2.4 meters east and dropped 400 kilometers of coastline by 60 centimeters. The coast went down. Then the water came up. Not a wall of surf, the sea rising and not stopping. In Miyako, the run-up reached 40.5 meters. 40 meters, a 12-story building of water. Around 18,000 people died. Along that coast stood the defenses, built over 80 years after the tsunamis of 1896 and 1933. Roughly 90% of them failed. 9 out of 10. In 1 hour.
80 years of coastal defense on this shore, and 1 hour took 9/10 of it out.
Look at what failure meant in Taro. Taro is the reason the rest of the coast changed. Look at how it was made. It is the same craft as everything that comes later. Built in stages from the 1930s and finished in the 1950s, largely by hand. A core of compacted earth and rubble faced with concrete, wide enough at the crown to walk on. Then, a second line, meeting the first in a V. Men carried stone. Concrete was mixed on site and placed in lifts. It took a generation, by hand, and it taught the town something nobody decided to teach it, that they were safe. When the shaking stopped, some went up onto the wall because from up there you could see the bay. Watch the sequence. The outer wall went first. The water came over it, filled the space behind, and pushed the inner wall from the side it was never designed to be pushed from. At least 140 people died in Taro.
My grandmother helped carry stone for that wall. We were told it was the strongest on the coast. I think that is why she stayed in the house.
And the biggest structure on the coast did no better. Kamaishi Bay had a breakwater listed in the Guinness Book as the deepest in the world. Foundation 63 meters down, 30 years to build, around $1.5 billion. The tsunami broke it, not overtopped, broke. The caissons were pushed off their foundation and scattered. More than 1,000 people died in Kamaishi. Now the exception. One village lost almost nobody, and the reason is a man who was laughed at for 40 years. Fudai is a fishing village of 3,000 people in a narrow valley. Kotoku Wamura was its mayor from 1947 for 10 terms. In 1896 and 1933 together, the sea killed 439 people there. 1967. The village built a seawall in front of the harbor, 15.5 meters. That was already considered excessive. He wanted more. A floodgate of the same height across the valley itself, where the river runs and the road goes. Because a wall with a hole in it is not a wall. Now the hard part. Somebody had to build it. A 15-meter steel gate across a river valley. The abutments go into the mountainsides on both flanks, because a gate is only as strong as the rock it is anchored to. The sill is a concrete apron across the valley floor, deep enough that water cannot scour under it. 2 towers, the leaf between them. hoisting gear on top. The river still had to run through it every day, so the gate had to be a hole that closes, not a wall that blocks. Construction ran from 1972 to 1984. 3.5 billion yen. For 27 years, it was a local joke. People said he built himself a gate instead of a school. Nobody says that now. Wamura died in 1997. He never saw it work. March 11th, 2011. Again, the water came up that valley to about 20 meters. The gate is 15 and a half, 5 meters short. Watch what happened. Some water went over the top. The gate broke the main thrust of it. Behind it, not one house was swept away. The village lost one man, a fisherman who went back to check on his boat. One. That is the whole casualty list.
One village behind a gate nobody wanted. 40 kilometers away, a town behind the strongest wall on the coast. Only one of them still has its houses.
The decision came within months. It was not popular. It was enormous. Rebuild the coastal defenses of the whole Sanriku shore. Not repair, replace, hire. The final program runs to about 395 kilometers of seawall, town by town, at 1.35 trillion yen, near $13 billion.
395 kilometers, town by town, bay by bay, no two sections the same.
Heights up to 14.7 meters, almost 15. The critics named it immediately, the Great Wall of Japan. They meant it as an insult. It stuck anyway. And underneath the argument sits an engineering decision almost nobody outside the industry noticed. They did not design these walls to stop another 2011. Read that again, because it changes everything that follows. Here is the decision nobody advertised. The country split tsunamis into two classes, 1 and 2. Level 1. The size that comes every few decades, the kind that hits perhaps once in 100 years. Level 2, the once in 1,000-year event, the kind that arrived in 2011. The concrete is for level 1, only level 1, nothing more. For level 2, the plan is that you run. That is the plan. Running. The wall is not there to hold the ocean out. It is there to slow the water and buy the minutes people need to get uphill. Everything about how these walls are built follows from that one sentence.
The wall is not there to hold the ocean out. It is there to buy the minutes people need to get uphill.
Now, the construction. The first thing to understand is that most of the wall is not the part you can see. You cannot stand concrete on sand and expect it to survive a tsunami. They learned that in 1 hour. The 2011 failures mostly did not crack. They were undermined, lifted, or pushed off their base as a unit. So the work starts below the beach, meters below it, under the sand, out of sight. Before any of it, the shape gets tested. In a tank. Sections are modeled in wave flumes. Long tanks where a paddle drives a scaled wave at a scaled wall, over and over, while sensors read the pressure on every face. That is how you find out that your design fails at the back rather than the front. Sheet piles go in first, sheet after sheet interlocked into the ground, forming a curtain deep enough to stop water scouring underneath the finished structure. The rig walks the shoreline and drives them one at a time. A vibratory hammer clamps the head of the sheet, shakes it into the ground, releases, swings back for the next. In soft sand, it sinks fast. In gravel, it fights, meter by meter. In gravel, it fights for every meter, one at a time, tens of thousands of them. In hard ground, each pile takes minutes of hammering, and there are tens of thousands of them along this coast. And that is only the curtain. Behind the piles, the ground itself gets treated, chemically, then mechanically. Cement grout is injected into the sand and gravel and mixed in place. Loose beach becomes something a foundation can sit on. Now it gets dangerous. Now the dangerous part. Then the excavation. Machines dig a trench along the shore. Pumps run continuously to keep it dry. And crews work in a hole below sea level with the ocean a few meters away, behind a temporary bund. And nothing here is built where it is convenient. Haul roads get cut along the shore. Temporary jetties go in where the road cannot reach. Barges bring rock in from the water side. The tide sets the working day, not the contractor. Twice a day the water comes up and the low sections have to be safe before it does. So the schedule is not written by the contractor. It is written by the moon. Twice a day. Every day. And the whole coast is still a seismic zone. Every tremor stops the crane, empties the trench, starts the inspection again. Only then does the concrete start, not before. It does not arrive by the truckload from a plant down the road, because there is no road and no plant. The contractor builds a batching plant on site, brings aggregate in by barge, and runs it around the clock. Concrete for a marine wall is not ordinary concrete either, not even close. It has to survive 60 years of salt spray without the reinforcement inside it rusting and splitting the structure apart. So the mixes carry blast furnace slag or fly ash. The cover over the steel is thicker than on a building, and every pore is tested. 60 years in salt. And for the sections that stand in the water, the concrete does not start on site at all. Watch where it starts instead. The big units are caissons, hollow reinforced concrete boxes, some the size of a building, cast in a dry dock or a casting yard on shore. They are built upright, floor by floor, reinforcement cages first, pours in stages so the concrete does not crack on itself. Then they are floated, actually floated, out to sea. Watch this now. A finished caisson is towed out with tugs, positioned over its prepared bed of graded rock, and sunk deliberately by flooding its compartments in sequence so it settles level. Divers check the seating. A diver on a caisson bed works in cold water with visibility in centimeters on a current, checking a rock bed by hand and by instrument, on a schedule set by the tide. Now watch it stop being a boat. Then the compartments are filled with sand and stone. The box stops being buoyant and starts being massed. One wrong angle on the way down, and a hollow box the size of an apartment block is sitting crooked on the sea floor. And it stays there. Half of what this coast cost is under the beach. The visible wall is the small part, and all of it happens on a coast that does not cooperate. And the coast does not cooperate. Winter brings wind off the Pacific, and concrete does not cure the way the specification assumes near freezing. Pours get heated, blankets go over fresh work, and the temperature inside the concrete is monitored until the forms can come off. Summer brings typhoons. Secure the site, move plant to high ground, pull the barges off, come back and see what the sea rearranged overnight. And the sea rearranges plenty. The wall itself is not one shape. Every town got a different one, because every bay behaves differently. Now the pieces themselves. Armor blocks come out of a casting yard near the works. Steel molds, concrete poured, units stripped after a day or two and left in rows to cure, hundreds at a time, standing in a field beside the shore like a stone army. Hundreds, for one bay. Each one is lifted by excavator or crane and set against its neighbors, interlocking, so the face is a mesh of blocks rather than a stack. And the sections themselves mostly arrive finished. Units are cast in a yard, cured, barged to the alignment and set on a leveling course by crane. Reinforcement spliced to the next unit and the joint poured on site so the line behaves as one structure. A single unit can weigh tens of tons. The crane sets it. 2 fitters guide it with taglines. A surveyor checks it. The crane lets go. Then the next one. Some sections are vertical faces. Some are sloped embankments faced with interlocking blocks. Some are a core of compacted earth armored on both sides, because the 2011 lesson was that water gets behind a wall and blows out the back. Watch where the water actually attacks. That is why the new design's armor the landward face too. If the sea comes over the top, the wall has to survive being hit from behind. The other lesson from 2011 was smaller and stranger. Many walls failed because their filling ran out of them. Water forced through the joints and washed the earth core out from inside. The structure collapsed into its own hollow. So, the new sections get geotextile membranes inside them, fabric layers that let pressure through but hold the fill in place. The rubble mounds at the base are built wider. The armor blocks interlock instead of merely stacking. Every one of those changes came out of a post-mortem on a wall that was already there. Every single one. Now the weak point. Between the sections come the openings, and openings are where walls die. Every road, every river mouth, every path a fishing boat takes. Each one is a gate. The gates are steel. They weigh tens of tons, and they have to close on their own. The 2011 disaster killed floodgate operators, men who drove down to shut gates by hand while the water was already coming. So the new ones close on a signal without a person going anywhere near them. Nobody drives to the coast. Nobody. Watch this now, because it is the detail that separates this from a wall. Look at how it actually closes. The gate leaf hangs in a steel frame set into the concrete. Hydraulic rams hold it up. Power comes from the grid, with a battery bank and a generator behind it. Because the first thing a magnitude 9 earthquake does is take the power out. The seals are the fiddly part. Always the seals. They decided. A gate that closes but leaks is a hole with a lid on it, so the sill and side channels carry rubber seals that must survive salt, sun, and sand for decades and still compress on the day. An earthquake trips the sensors, the alarm goes to the gate controllers, and the steel comes down while the town is still shaking. No approval, no operator, no drive to the coast. Along the rebuilt coast, there are hundreds of these gates. Each one is a hole in a 14-meter wall that has to shut in minutes and then hold against a moving sea. And then they have to be exercised. Forever. Now look at what a single gate actually is. Look at what a single gate actually is. The leaf is fabricated in a shop, not on the coast. Plate steel cut, rolled, welded into a box girder, blasted clean and coated in layers that must hold against salt for decades. Then it comes to sight on a low loader. The frame goes in with the concrete. Before the pour, to the millimeter, anchor bolts and embedded plates set in the formwork before the pour, positioned to a few millimeters, because a frame out of true is a gate that jams. Watch the lift. Then the lift. A crawler crane picks the leaf and holds it over the opening while fitters guide it down the channels by hand, between tides, in a working harbor. And then the trial closures. Dry runs, timed. Power cut deliberately to see whether the batteries take it. Sensors triggered to see whether the alarm reaches the controller. If it does not close in the time the drawings promise, it does not get accepted. A gate that has not moved for 2 years will not move on the day. So crews run them, grease them, replace seals, test the batteries and the sensors, and log all of it. And it never finishes. Sensors went in with the concrete, inside it. Strain gauges, tilt meters, tide gauges, tied back to prefectural monitoring. So a section that starts to move is noticed before anybody sees a crack from the road. That maintenance bill runs forever. It is the part of the project that has no end date. Now the part that decides whether any of it is worth anything. Watch what happens if it does not. Every stage gets checked. Pile positions surveyed. Concrete cylinders crushed in a lab to prove strength. Welds on the gate frames tested. Caisson beds measured by divers and remeasured after settlement. A section that fails the check comes out again, because a 400-kilometer defense is only as strong as its worst joint, and the ocean will find that joint without any help from anybody. And in Kamaishi, they went back to the breakwater the sea had broken. The rebuild is not the old structure again. Watch what they changed. The new caissons are heavier. The mound under them is wider, and the units are tied to each other, so a single box cannot be pushed out of the line on its own. That is the same idea as the geotextile in the earth walls, at 100 times the scale. Stop the structure failing one piece at a time. Work went on through the following decade in a working port, with fishing boats using the channel throughout. Because the arithmetic on that breakwater was never zero. It broke, and it still cut the wave down and bought minutes before it did. A defense that fails can still be the reason somebody made it up the hill. That is not nothing. Ask Kamaishi. Look at what one unit costs in work. Casting a caisson that size is its own yard operation. A basin, reinforcement tied by hand, concrete placed in continuous lifts so there is no cold joint through the wall of the box, then weeks of curing before anybody floats anything. Then there is the harder half of the job, the part where they move the ground itself. Rikuzen Takata lost more than 1,700 people, around 8% of everyone who lived there. 80% of its residential area was destroyed, and the 70,000 pines of its coastal forest, planted in the 17th century as a defense against the sea, went in an afternoon. The town could have rebuilt where it was, behind a wall. Then somebody proposed something else entirely. Instead, they decided to lift the whole town about 10 meters. The whole town, not the buildings, the ground itself, all of it. To do that, they took the top off a mountain. Watch that sentence again. Crews stripped and blasted the hillside. The material came down on belt conveyors running nearly 3 kilometers. 10 hours a day, 6 days a week, for years. Think about the arithmetic. A city center raised by 3 stories, one conveyor load at a time. Bulldozers spread it, rollers compacted it in layers, surveyors checked levels, and the mud plain where a town used to be became a plateau above the reach of the water. And you cannot simply tip earth onto a coastal plain and build on it. Fill settles. Always. So the ground is loaded, left to compress, drained with vertical wicks, tested, and only then released for construction. The town's services went in before the fill went on top. Water, sewer, power, all buried in a plateau that did not exist 5 years earlier. Now the part that decides the next 30 years. And the fill had to come in the right order. Coarse rock at the bottom for drainage, finer above it. Each layer spread thin and rolled until a plate test says it will carry a building. Get that wrong, and the town settles unevenly for 30 years. And every road and pipe in it cracks. The old ground is still down there, under everything, still there. Somewhere under a supermarket car park is the street plan of the town that was washed away, buried, not removed, and a 12.5-meter seawall went up in front of it anyway. They raised the ground 3 stories. Then they built a wall in front of that. Neither one alone was considered enough. And the conveyor itself was a construction project. Towers, belts, transfer stations, a crossing over a river, built to run for years and then be taken away. When the fill was finished, it came down. The mountain it fed from is still short of its top. and the work went on inside a living town.
Understood.
Roads had to stay open while the ground under them was replaced, so the town was rebuilt in strips. One section raised and released. Traffic moved onto it. The next stripped and filled. Temporary schools and shops sat on the old level the whole time, waiting for ground that did not exist yet. And every cubic meter was measured.
32.4.
Load tests, settlement plates, monitoring points read week after week, because a plateau that is still moving cannot carry a town. Now the cost nobody put in the budget. In Taro, the new wall is up to 14.7 meters high and runs for over 2 kilometers. At its base, residents tilt their heads back to see the top. To look at the ocean, they climb more than 30 steps to a viewing platform. 30 steps. To see the sea they live on. In Osabe, a 12.5-meter barrier went up in front of the water. Kazutoshi Musashi described it plainly. It looks like the wall of a jail. Oyster fisherman Atsushi Fujita, whose city lost nearly 2,000 people.
I used to check the sea from my kitchen. Now I check a wall. If something is wrong out there, I will find out when the siren goes.
And some communities refused outright. A handful of towns fought the plan down, cut the heights, or rejected the wall and moved uphill instead. Now look at what is actually finished. Around 395 kilometers of new seawall, 1.35 trillion yen. Structures up to 14.7 meters tall, where 4-meter breakwaters used to be. Hundreds of automated gates that close without a human being. An entire city center lifted 3 stories onto ground that did not exist before. And this is where it stops being a triumph. Because the towns behind the walls did not fill back up. Not even close. Rikuzen Takata rebuilt on its plateau, and thousands who lived there never came back. 10 years on, more than 70,000 people were still displaced across the region. You can defend a town. You cannot order people to return to it. So what did $13 billion actually buy? Not safety from the sea. Nobody who built this claims that. The walls are rated for the tsunami that comes every century, and everyone knows the other kind is coming. Japan's forecasters expect a megaquake in the Nankai Trough within the lifetime of most people alive today. Now, the part that undoes the title. This is not a barrier against the ocean. It is a machine for making time. That is all it is. That is enough. The whole 400 kilometers exists to do one thing. Slow the water for a few minutes so the people behind it can be somewhere else when it arrives. Concrete cannot save a coastline. It can only lend it minutes. And in Fudai, the gate that made a mayor a laughingstock for 27 years is still standing across the valley. It is inspected. It is maintained. It gets tested every year, because the sea that came in 1896, and again in 1933, and again in 2011, has not agreed to any of this. It is simply between visits